So let's take a look at finding the radius and interval of convergence of a power series. So remember that in a power series we must use either the ratio or the root test. So to give a brief review here, for the ratio test, let's say we have the series of a sub n. So we have to set the limit as n approaches infinity of a sub n plus 1 over a sub n. Take the absolute value of it. Now, if that limit is less than 1, we know the series will converge. If the series is greater than 1, or if the limit is greater than 1, we know the series will diverge. And if the limit is equal to exactly 1, then the series, once again, is inconclusive. And we have to try a different series. But since we're trying to find the radius and interval of convergence, we're basically looking for where the limit is less than 1, because we know at that value it will converge. So let's say for number 1 we have to find the radius and interval of convergence of the infinite series from 1 to infinity of x to the n over square root of n. Now it isn't really a good idea to use the root test here, so we have to use the ratio test. So once again, for the ratio test, we have to set the limit as n approaches infinity of x to the n plus 1. So wherever we have n, we're going to replace it with n plus 1 over the square root of n plus 1, divided by just our regular sequence, x to the n over square root of n. Remember, if I divide by a fraction, I can multiply by its reciprocal, and we have to set the absolute value. So we get the limit as n approaches infinity of x to the n plus 1 over the square root of n plus 1, multiplied by the reciprocal, square root of n over x to the n. So to simplify, since these powers are being added, I can break them up. So we have, if I rewrite the limit down here, I can rewrite x to the n plus 1 as x to the n times x to the first, or just x, over the square root of n plus 1, multiplied by the square root of n over x to the n. Notice the x to the n's will cancel, and I'll rearrange the fractions so that I have two separate fractions being multiplied by each other, so I can separate the x's and the n's. So I will just rewrite it as the limit as n approaches infinity of x times the square root of n over the square root of n plus 1. And the reason why I'm doing that is because we're setting the limit as n approaches infinity. So basically I have to plug in infinity to wherever I have n. Now the limit as n approaches infinity of the square root of n over the square root of n plus 1, since we have the same powers of the square root of n on the numerator and square root of n on the denominator, the limit to infinity is just going to be 1. So we have the absolute value of x times 1, or just x. So we have the absolute value of x times 1, or just x. And remember, in order to find the interval and radius of convergence, we must set it less than 1. So the absolute value of x has to be less than 1, because we know by using the ratio test, if the limit is less than 1, it will converge. So we have to find for what values of x is the limit less than 1, or in this case the absolute value of x. So in order to get rid of the absolute value and solve for x, all we have to do is put it in this form, where we put the negative version and the positive version. So the negative one has to be greater, or x has to be greater than negative 1 and less than 1. So that's how we remove an absolute value. And so now that we know that x has to be between negative 1 and 1, so our interval is going to be from negative 1 to 1. So even though we know that x has to be between negative 1 and 1, well, what we don't know is that if it can include these endpoints. So in order to test that, all we have to do is plug these endpoints back into the series for x and test the series for convergence or divergence. So I'm just going to go ahead and start with plugging in the value of 1. So if we do that, we get the series from n equals 1 to infinity of, remember we plug in 1 for x and just x, so 1 to the n over the square root of n. Now, no matter how big of an n we have, 1 to the any number is always going to be 1. So I'm going to rewrite it as this series from 1 to infinity of 1 over, and I'm going to rewrite square root of n as n to the 1/2. And now this looks like a p-test. So if we put p as our exponent, so exponent is obviously 1/2. So if p is equal to 1/2, 1/2 is obviously less than or equal to 1. So we know the series will diverge by the p-test. So if we plug in 1 for x and it diverges, that means we cannot include 1. So it's just going to be left as a regular parenthesis. Now if it included 1, we would change it to a closed bracket. But since it doesn't, we just leave it as a parenthesis. So now let's test -1. So if I plug in -1 to the series from 1 to infinity, we have -1 to the n over the square root of n. Notice we have -1 to the n, so this is an alternating series. So we can just set the limit as n approaches infinity of everything except for the alternator. So we basically have to set the limit of 1 over the square root of n. And the limit is obviously 1 over the square root of infinity, which is equal to 0. So we know the series converges by the alternating series test. So since it does converge when we plug in -1, we just replace it with a closed bracket, because we know it includes a -1, but it does not include 1. So that is our interval of convergence. So now, in order to find the radius of convergence, we must know what the center is. And this is pretty easy. The center is basically what the number between the two endpoints. So between -1 and 1, obviously the center is 0. And now in order to find the radius is basically the distance from the center to either one of these endpoints. And the radius is always going to be positive, so we can just pick 1. And the distance between 0 and 1 is obviously 1. So our radius is going to be equal to 1. Now for number 2, let's say we have to find the radius and interval of convergence of x to the n over n factorial. So once again, we have to use the ratio test because the root test doesn't really work here. So the limit as n approaches infinity of the absolute value of x to the n plus 1 over n plus 1 factorial divided by just the regular sequence x to the n over n factorial. So then if I divide by the fraction, I can multiply by the reciprocal. So we get the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial multiplied by the reciprocal, so n factorial over x to the n. So once again, I can simplify these by splitting up the exponent. So we get the limit as n approaches infinity of the absolute value of x to the n times x to the first, or just x, multiplied by n factorial. And n plus 1 factorial, I can also split that up and rewrite it as n plus 1 times n factorial. So if I rewrite it like that, over n plus 1 times n factorial, multiplied by n factorial over x to the n. X to the n's will cancel, and the n factorials will cancel. So we're left with the limit as n approaches infinity of 1 over n plus 1. And remember, I'm going to split up the n's and the x's times x. So when I plug in infinity for n, we obviously get 1 over infinity times x. and 1 over infinity is 0, and 0 times x is 0, and the absolute value of 0 is 0. So we get 0. Now, once again, in the ratio test, we have to set it less than 1, or set the limit less than 1 to find where it converges. And notice 0 is always going to be less than 1, which means that this limit, or the series, converges for all values of x. Now, if it converges for all values of x, that means our interval of convergence is from negative infinity to infinity, and this means our radius of convergence is also infinity. And that's because the distance between negative infinity and infinity is 0, so our center is basically 0. And to go from 0 to 1 over endpoints, it's basically infinity. So this is why our radius is infinity as well. So now let's say for number 3 we have the series from 1 to infinity of n factorial times 2x minus 1 to the n power. So once again we have to use the ratio test. So the limit as n approaches infinity of n plus 1 factorial times 2x minus 1 to the n plus 1 factorial, or to the n plus 1 power, over n factorial times 2x minus 1 to the n power, and the absolute value of the entire thing. So here I can basically just expand a bunch of these exponents. So I'll expand the n plus 1, and I'll also expand the factorial, so that I can simplify and cancel out some of these terms. So the limit as n approaches infinity. Now, in order to expand n plus 1 factorial, I can rewrite it as n plus 1 times n factorial times, I'll expand 2x minus 1 to the n plus 1 power as 2x minus 1 to the n times 2x minus 1 to the first, or just 2x minus 1, over n factorial times 2x minus 1 to the n power. So the factorials will cancel, and the n powers will cancel. So we're going to be left with the limit as n approaches infinity of the absolute value of n plus 1 times 2x minus 1. So when I plug in infinity for n, infinity plus 1 is obviously infinity. So we'll get the absolute value of infinity times 2x minus 1. Now infinity times any number is obviously still infinity, and the absolute value of infinity is infinity. So in the ratio test, once again, we're going to set it less than 1 to find the interval of convergence. And notice infinity is never going to be less than 1. And be careful here, because this means that the interval of convergence will be for no x value except for one x value. And that x value is when we set our x equation equal to 0. So if I do that, 2x minus 1 equals 0, which means 2x equals 1, and then x will equal 1/2. Now the reason why it's this one x value is when I plug 1/2 in for x, we'll get obviously infinity times 0. And infinity times 0 is technically 0. And so if we set 0 less than 1, we know this is a true statement. So it will be for no x value except for that one x value where it equals 0. So our interval of convergence will only include 1/2. And remember, whenever we get in infinity, our radius will always be 0, since it includes no value except for that one value.